Happy Denim Day! Well, it all depends on what day you're watching this, but Denim Day celebrates the use of jeans. So hopefully you're wearing jeans today. Celebrate uh, Denim Day. But anyway, we're going to do section 11.1, very beginning of chapter 11. In chapter 11, it's all about, really mainly about volume and surface area. And section 1 kind of starts us off with this idea of space, figures, and cross sections. So we'll see what that is. Your goal for this section, two of them. One would be to recognize polyhedrons and their parts, and one is to visualize cross sections. So yes, cross sections has a lot to do with visualizing. So in a video, it might be hard to visualize, but maybe using an actual shape would help. But anyway, try your best to visualize through this video. But anyway, here we go. We're going to start it off. A polyhedron. I feel like it's called a polyhedron as well other places, but polyhedron, I believe, is more commonly used. Polyhedron is spelled, if you can't read that, P-O-L-Y, poly, H-E-D-R-O-N, polyhedron, is a space figure or a three-dimensional figure, so it's 3 dimensions, whose surfaces are polygons. All right. Um, each face is a polygon, so the faces are polygons. Um, the segments that are formed by the intersection of two faces. So if you have the two faces, they intersect at one of these. These are called edges. Real fancy term there. And then the points where 3 or more edges intersect. So we have this, this, and this all intersect at this point right here. That is called a vertex. No new words here, but that's how you describe a polyhedron or a three-dimensional prism. Prism are oftentimes used for these. So example 1, how many vertices, edges, and faces are in the polyhedron at the right? List them. So vertices, edges, and faces. I'm not going to list them all, um, but we have one on the top, 2 on the sides, 1 on the bottom, and 1 on the back. So that makes 1, 2, 3, 4, 5 faces. Edges, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 edges. And the vertices. Vertices we have. I'm going to use a different color for vertices. 1, 2, 3, 4, 5, 6. 6 vertices. Next question is segment TV an edge? So TV, looking for TV. I'm going to erase all this. And certainly if you draw a TV, it'd go from here to here. Is that an edge? Explain why or why not. Well, no, it would not be an edge. And the reason is because it's not where two faces meet. It's not a segment where two faces intersect. That's actually just a segment that you draw across a face. So it's not an edge. All right? So that is the idea of faces, edges versus vertexes or vertices. Now, we have a key concept, and this is a sweet one. Euler's Formula. So if we read up here, Leonhard Euler, he is actually a very famous mathematician. Uh, he's a Swiss mathematician, like Swiss cheese or Swiss Miss. But anyways, he discovered a relationship among the numbers of faces, vertices, and edges of any polyhedron, and he made a formula. So it's kind of interesting. The sum, let's look at this. The sum of the number of faces and vertices is 2 more than the number of edges. So if you add up the faces and the vertices, that's going to be 2 more than the edges in every single polyhedron. I mean, this is just total experiment here because it works for every one. So even if you can't see the whole polyhedron here, you don't have to count all the faces and everything. We're going to use the formula to find the missing number. So I'm going to actually use the formula right here. Faces we don't know, so we're going to say F. edges, so faces plus vertices is 20, plus 20, would be equal to the number of edges plus 2. So you can just solve for f. You can look at it and you can probably figure out pretty quickly that the number of faces is going to be 12. But if you wanted to, we'd have f plus 20 equals 32. Subtract 20. Woo! Subtract 20 from both sides. You get the number of faces is equal to 12. So there are 12 faces on this polyhedron. So you said again, I'm just looking for edges this time. 20 plus 12, so faces plus vertices, equals number of edges plus 2. So just subtract 2 from both sides. This is 32 minus 2. We have 30. All right. So that is Eulers. It's pronounced Eulers. It looks like Eulers, but it's Eulers formula. All right. In 2 dimensions, Eulers formula reduces f plus v equals e plus 1. So if it's 2 dimension, it doesn't work quite like 3 dimension. 2 dimensions, just slightly different. So, example 3. How can you verify Euler's formula for a 2-dimensional net of the solid at the right? So, when we're saying a 2-dimensional shape, we're taking this and we're making it a net. So, in other words, here, let's make the net then. So we have this base would be the bottom one like that. We have a side that goes out like, say it's like this. Side over here that goes out like this. And we've got this one right here. We got this one right here. Do I have enough? No, we're missing one little one on the top. So, interestingly enough, the Euler's formula for 3 dimensions would work on this 3-dimensional figure. But if we look at this and actually count, the number of faces would be 1, 2, 3, 4, 5, 6. So we still have the same amount of faces. So we have 6. The number of edges now gains 1. Or sorry, yeah, the number of edges gains 1. That's why we take 1 away from here. The number of edges gains 1. We'll do the vertices too, though, right away. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. See if I'm doing this right. I might be doing it wrong. But anyway, edges, we gain 1 because we're splitting this one in half, this one that would be touching here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And that actually does work out. So it changes the whole dynamic when you make it 2-dimensional. There's a whole bunch of more faces, or vertices and edges, but we have 20 over here is equal to 20 over there, and that's how we just verified Euler's formula for 2-dimensional figures. Interesting, huh? All right, so those are, we're looking at some, now we're going to look at the other part, the cross-section part. So, a cross-section is the intersection of a solid and a plane. So we'll say that's a cross-section. And I kind of picture this as when you have that that trick where magicians always cut, they always play that where you cut a person in half, and they're in this box, and then they do this little thing where they cut right in half. They just cut right through this box. That's what I picture a cross-section being. It's an intersection of a solid and a plane. So that thing that you're cutting the person, well, the illusion of cutting the person in half would be the plane that's cutting right through a solid. So if you picture it, the cross-section part is just the part inside of it formed by that cut. So this triangle that's formed on the inside of there when you're cutting through a shape would be called the cross section. So it's kind of something about visualizing. You have to really visualize it. So for the solid at the right, look at an example for it. What is the cross section formed by each of the following pieces? So a horizontal plane. Let's say you're taking a shape and you're cutting it right through here. It would make a circle. The part in the inside would make a circle. How about a vertical plane dividing it like this? If you were to picture what's inside of there that would be cut in half, what would that make? In my experience, I think that would make, you kind of pull it out, it'd look like this. The bottom part is a little like that, it looked like this. And that would be a trapezoid. And again, this has to do with visualizing. Let's go to example 5. What is the cross-section formed by a plane that is tilted and intersects the front, bottom, and right faces of the cube? That's tough because it's hard to draw one. So the front, bottom, down there, and the right. So it's got to kind of go through. Um, this is really hard to visualize, but it's going to go, if this is the bottom, we'll go like this. So it's going to kind of cut off this. So that's the bottom. It's going to come up and do this and do this. It's going to kind of cut off that bottom, that whole right, this corner right here. That would go through those three faces, and it'll form a triangle. It'll form a triangle, interestingly enough. That would be the cross section. I want you to do this one on your own. What does the cross section look like for this figure? If you picture it, what do you think that cross section looks like? So go ahead and describe it. Well, I think it would look like this. Since the top part up here would be a little bit smaller because it's towards the top, the bottom part down here it'll be a little bit bigger since it's the bottom and they're kind of closing off. So it would be a trapezoid again. Again, it's all about visualizing it. If you have questions on this, ask, but it's all about visualizing these cross sections. So last thing I'd like to look at is just this error analysis. It says identify the error in planning or solving the problem. Don't believe this has to do with cross sections, but it has to do with going back to the faces, edges, and vertices and using Eulers method, formula. So I want you to do this error analysis, and once you're done with that, answer these last two questions. What are the three parts of polyhedron that are related in Eulers formula? How are the number of faces, vertices, and edges of a polyhedron related? So that has to do with Euler's formula. And what is a cross section in your own words? And that's it for section 1. Just visualizing things in geometry that are three-dimensional in particular, and kind of relationship between different parts of these three-dimensional objects or polyhedrons. So that is it. Go back and take a look at your two goals and see if you met these goals, if you understand them, or if there's something you have questions on. Have a